Hello students. Yesterday we have seen the property of nucleus which is important for NMR, that is the spin. Now today we will see the next points related to the NMR. Yesterday we have seen that if the nuclei are present in absence of the magnetic field and if they are present in presence of a magnetic field, what happens to them? Check this case where the nuclei are present in absence of magnetic field. They spin in random direction, random orientations are there and all are spinning in different ways. This means that clockwise rotation or clockwise spin motion and anti-clockwise spin motion are of equal energy. As soon as we place these nuclei in contact with the external magnet or in magnetic field, look at this image. It is present in contact with external magnet. Then some of the nuclei have their spins or magnetic movements in upward direction, that is towards the in the direction of a applied magnetic field, and some of the nuclei are having their magnetic moments in a downward direction, that is in opposite direction to the applied magnetic field. Why this happens? Some of the nuclei spin in a clockwise direction. Look at this. These two nuclei or this one more is there. These are spinning in a clockwise direction, and at the same time these two move in a anti-clockwise direction. Now the magnetic moments for these three nuclei are in upward direction, or that is in parallel direction to the applied magnetic field, and the magnetic field or magnetic moment of these two nuclei which are moving in a anti-clockwise direction, their magnetic moments are in opposite direction to the applied magnetic field. This means that the two orientations are of different energy. Let us see here, the one which is in parallel direction to the applied magnetic field, we call that as a alpha spin state, and the one which is in or which is spinning in opposite direction, that we call as a beta spin state. That is, now the energy of these two spin motions or spin orientations are different. One is of lower energy and other is of higher energy. There is a difference in the two energy levels. Once the nucleus is placed in a contact with external magnet, the spinning nucleus under the influence of external magnet or magnetic field acquires another motion that is called as a precessional motion, and it starts precessing with certain precessional frequency. Precessional frequency depends on the strength of the applied magnetic field. What is this precessional motion? Let us see in a short video. So we have seen the how nucleus precesses, precessional motion. Last year I had told you that precessional motion is very similar to the motion of a child's top. So spinning nucleus gets another motion, and precessional motion. That precessional motion depends on the strength of the applied magnetic field. Nucleus will absorb the radio frequency radiations of frequency equal to its precessional frequency. Let us see this. Energy difference is proportional to the magnetic field strength, which is given by the formula delta E is equal to h mu, which is equal to gamma h upon 2 pi b0. This is the energy difference equation. That is, the energy difference between the alpha spin state and beta spin state is equal to this. And a nucleus absorbs this energy, and then it goes to the excited state, beta spin state. After some time, it releases the energy and the signal is detected in the NMR. This is the simple process that occurs in the NMR. Let us see. So this relationship between the energy levels and the external magnetic field strength. Look at this arrow. External magnetic field strength is increasing from left to right, and energy is increasing from bottom to top. Now see this, as soon as the external magnetic field strength is increasing, the difference in the energy level between alpha and beta spin states. Look at this. This is alpha spin state. This is beta spin state, where the magnetic moment of the nuclear magnet is parallel to the applied magnetic field, and this is in opposite direction to the applied magnetic field. So this is your plus half, this is your minus half spin state. Look at this. At this point, the difference between the energy levels is very small when the external magnetic field is small. But as I am increasing the external magnetic field strength, the difference between the two energy levels is increasing. Now what I have said, that the stronger the applied magnetic field, greater will be the difference between the two possible spin states. That is, delta E is the function of B0. B0 is the strength of the applied magnetic field. Energy difference of the energy levels also depends on the magnetogyric ratio of the nucleus. That is, now we can write the equation as delta E is equal to, or it's a function of gamma into B0, which can be expressed in the form of h mu. Delta E is equal to, or the final equation can be written like this: delta E is equal to gamma into h upon 2 pi b0. This is the equation. Now sometime back I had told you that the spin orientations are quantized. Quantized means what? Now I will tell you. This finally, this equation, frequency for frequency, it is converted into gamma upon 2 pi into b0, where h will get cancelled. Now gamma, this gyromagnetic ratio, is the property of particular nucleus, and B0 is the magnetic field strength. So if I place B0 constant and gamma is changed, gamma is changed means what? The nucleus is changed. Then what will happen? The energy is going to change. Or if I keep gamma constant and I vary the B0, the energy is also going to change. But these, if both of these are kept constant, then we'll have a certain or definite value. Or if I'm changing these things, it will be multiple of h into 2 pi. That's why we call it as a quantized. It is having definite frequency. Now let us consider for proton. Different field strengths are there. That is B0 is same, and the frequency. I have written these values for proton. If the B0 field strength is kept constant of 1 Tesla, the proton will absorb or will precess at the frequency 42.6 megahertz. And if the magnetic field strength is 1.41 Tesla, the absorption frequency or the precessional frequency of that nucleus is 60 megahertz. This means that as I'm going to change the strength of the applied magnetic field, the absorption frequency is changing. Let us look at this. These are the different nuclei and their natural abundances, and at different field strengths, what are the absorption frequencies. Let us consider this H1 proton. If the applied magnetic field strength is 1 Tesla, then its frequency is 42.6. If it is 1.41 Tesla, the absorption frequency is 60 megahertz. If magnetic field strength is 2.35 Tesla, the absorption frequency is 100 megahertz. This means that as you are changing the magnetic field strength, the absorption frequency is changing. As you are going to increase the magnetic field strength, the absorption frequency is also changing. That is, the energy difference between the alpha and beta spin state is increasing. Let us take this carbon 13. Carbon 13 also, you are looking at this magnetic field strength 1. Its absorption frequency is 10.7. Now look at the difference. When proton was observed at magnetic field strength 1 Tesla, its absorption frequency is 42.6 megahertz. And when the carbon 13 is observed at 1 Tesla, its absorption frequency is 10.7. This means that the energy difference between the alpha and beta spin states with respect to proton and with respect to C13 is not same. The energy difference for proton is 42.6 megahertz at 1 Tesla. At the same time, for carbon 13, it is only 10.7 hertz at 1 Tesla. This means that the absorption frequencies of carbon and H1 or C13 and H1 are not same at the given magnetic field strength. Why? What is the problem? Problem is that the magnetogyric ratio of proton is 267.53 while that of carbon is 67.28. If you remember the equation, delta E is equal to h mu into gamma h upon 2 pi into B0. If magnetic field is kept constant, let us see in our this example 1 Tesla. The gamma is changing, therefore the energy difference is changing. And this is the reason why C13 is not interfering in the spectrum of H1 or H1 is not interfering in the spectrum of C13. That is, the signal of proton will not, or the spectrum of the proton H1 will not have the signals corresponding to C13. This is because the absorption frequencies of two nuclei are totally different. Now if you see fluorine 19, at 1 Tesla, fluorine 19 is having the absorption frequency 40.0, which is very close to H1, but still the two nuclei signals are not interfering in one another's spectrum. If you look at this, the gyromagnetic ratio of H1 is 267.53 and that of fluorine is 251.7. So smaller changes in the gyromagnetic ratio are very important. They do not allow the nuclei to interfere in one another's spectrum. This is the process of absorption of the energy. This is the nucleus which is precessing in a clockwise direction, that is, it is in a plus half spin state, or we can say that it is in a alpha spin state, or in short we call it as a ground state orientation. The spinning nucleus will start precessing under the influence of external magnetic field and it will have a certain precessional frequency. if we provide the radio frequency radiations of that frequency, let us see this. In this case, the precessional frequency is 60 megahertz. Precessional frequency is represented by omega. It is of 60 megahertz. And now I am providing the radio frequency radiation, whose frequency is also 60 megahertz. At this point, the nucleus will absorb the energy from the radiation. At this point, the magnetic field or the magnetic field of the nucleus is in resonance with the magnetic field of the radiation. And so the two fields are in resonance with one another. And nucleus, what we say, nucleus is in resonance with the radiation. It absorbs the energy, or energy is transferred from radio frequency radiations to the nucleus. Nucleus absorbs the energy and now it goes to the excited state. Immediately it changes its spin direction. Now it is spinning in a anti-clockwise direction and it is a minus half spin orientation. That is, it's a beta spin state. So this is how the absorption of the radiation takes place, or the process of nuclear magnetic resonance occurs.